So in this video, we're going to talk about finding center of mass. We're going to apply calculus techniques, well, integration techniques, to find sort of the balance point of objects. And for this, we're going to pretend that you're in a boat. And there are a bunch of different objects of different weights in this boat. And I know I have these labeled as M, but because we're on Earth, I'm going to treat mass as the same thing as gravity. Clearly that's not exactly the case, that the force of gravity is a force, whereas mass is independent of the gravitational field that you're in. This is a made up example anyway, so don't worry about it. But let's say that you're sitting at the coordinate -1, -1, and you have a mass of 150, or a weight of 150. Your younger fisher mate, say it's your niece or your nephew or your little brother, has a mass of 40. You have a jug of water at 1, that weighs 10. You have a boat's anchor at -1, 2, way up here, that has a mass of 40, and also the motor back here that has a mass of 40. And we want to know, is this boat going to tip over? Where's the center of mass given this collection of items? And when thinking about center of mass, there are a couple of things that you have to consider. So, like, thinking about a teeter-totter, for example, let's say that we have a perfectly aligned balance here. And if you put two objects on it that are of exact equal weight, you notice that the teeter-totter is going to balance. Like, let's say this is of mass M, and this is also of mass M. But even if you keep the masses the same, and you sort of push one to the edge of the teeter-totter, you'll notice, let's see if I can make this teeter-totter work without these masses like falling off. Even if they're still the exact same weight, being further out is going to exert more angular force on this balance, and the teeter-totter is going to tip. And we measure that in a really specific way called a moment. And if you've taken a physics class, maybe you've talked about moments. So here I'm thinking about moments with respect to just this one balance point, but on a 2D plane we talk about moments with respect to a given line. So a moment, m sub L, is the mass of an object times the distance to the line. So you'd see with this one, because the distance is greater, even though the mass is the same between these two objects, the distance is greater, so the moment for this object is going to be greater with respect to, not a line, but this triangle balance point. In particular, when we start looking at our Cartesian coordinate system, if we have moments with respect to the x-axis, so let's say we have some object over here, its moment with respect to the x-axis is going to be its mass times the distance to the x-axis. And the distance to the x-axis is given by its y-coordinate. Like, how far is it from the x-axis? It's whatever its y-coordinate is. This is the point x, y, and it has mass m. Similarly, the moment with respect to the y-axis, with respect to this line, is going to be the mass of the object times the distance from the line, which, of course, that distance is measured in x. It's sort of confusing because m sub x has a y in it and m sub y has an x in it, but really once you draw a picture, I think that it's really intuitive that the moment with respect to the y-axis is just the distance away from the y-axis, so that's why we would need to have an x in there. So let's return to our boat example. We have a whole bunch of different masses, and so we're going to compute. Let's start off by doing m sub y for each of these objects. And I guess I could go in the same order that I had it listed on the sheet. That m sub y of yourself, starting down here with my person, it's going to be, recall m sub y again is the mass of the object, which is 150, times the distance that object has from the y-axis, which in this case, although the distance is only 1 unit, we're going to maintain the -1 because we want to actually have a sense of space, right? So 150 times -1, that it's behind the y-axis. That's the moment for you, with respect to the y-axis. But we want to know over every single object, and so we're actually just going to do a summation of all of these. So your weight times your distance from the y-axis. Let's see, let's do the anchor up here is 40, and it's also at -1. We have, let's see, the jug of water, which is 10 at 1. We have the little kid, whoops, I'm running out of space, 40 at 1. And then we finally have the motor, which was 50 at 1. And I can plug all this into my calculator because I don't want to have to think too hard. 50 minus 40 plus 10 plus 90. Oh, it's -50. Oh, here's my calculator. -150 minus 40 plus 100. 10 plus 40 plus 50. I could have done that in my head. Sorry. So m sub y is -90. And we'll talk about what this number means in a second, right? Well, this is just the sum of all of the moments. Is that telling me my center of mass? Like, what are the units on here? In order to actually find the center of mass, we're going to have to find the sum of the masses of the entire system. So maybe I'll write that down here. The center of mass with respect to the y-axis is going to be all of the moments, m sub y, divided by the total mass of the system. And I might even write the sum of m, because this is indicating the total mass. And in this case, our m sub y we found was -90. And our total mass of the system in this case is the sum of each of the masses of the individual objects. 50 plus 40 plus 10 plus 40 plus 50, which is 140 plus 150 is 290. And this will give me my y-coordinate, my distance over from the line of the y-axis. So it's going to be the x-coordinate of the center of mass with respect to this y-axis. So what is -90 divided by 290 is -0.31. Let's do the same thing and calculate all the moments with respect to the x-axis. Now I'm going to have to think about vertical distance. How far are they from the x-axis? I'm 150 pounds and I'm down 1 unit. The anchor is 40 pounds and it's up 2 units. The water bottle is 10 pounds and it's up 1 unit. The little boy is 40 pounds and is down 1 unit. And the motor is 50 pounds and it's down 3 units. So I see that altogether my moment with respect to the x-axis of this entire system is going to be -150. Can you read this? I guess not. Plus 2 times 40 is 80, plus 10, minus 40, minus 150. So this is at -250. And our center of mass, m sub x, divided by the mass of the entire system then is -250 divided by 290, which is still a little less than 1. I can plug that into my calculator. And it's going to be about equal to negative 0.862. So if I wanted to draw graphically on this where the center of mass is, that this is the x-coordinate of the center of mass, and this is the y-coordinate of the center of mass. And why does that make sense? I was computing this with respect to the y-axis, so I'm saying that I'm over negative 0.31. And because this is with respect to the x-axis, this is a y-coordinate of negative 0.862. So that means my center of mass is given by the coordinates negative 0.31, negative 0.862. So although this boat isn't perfectly balanced, it's not going to be like, here's my center of mass. I'll put an X from our center of mass in this boat-shaped thing. That's not perfect. It's going to be a little tilted back into the side, but it doesn't look like my boat's going to flip over.